Hello, Coach Travis here with another calculus video. So what we've got here is a problem about the end behavior of a function. So end behavior is all about what happens, what's the limit. Well, maybe even forget the limit, just the end behavior is all about what happens when x gets really big or when x gets really, really negative. So formally, what that is that's a limit. You know, it's either the limit as x goes to infinity, that's the case when x gets really, really big, or it's the limit as x goes to negative infinity, because that's what happens when x gets really, really big, really negative, sorry. So there's always, in behavior, there's two ends, right? There's a left-hand end and a right-hand end. And the right-hand end is the limit as x goes to positive infinity, and the left-hand end is the limit as x goes to negative infinity. So this is a question, you know, when it asks me to find a limit as x goes to positive or negative infinity, that's a question about the end behavior. All right, well, okay, so now that we've established that, how do you actually answer this question? So the secret to doing things like this is when you're dealing with a polynomial or a rational function, well, this is a polynomial, then the only term that matters is the dominant term, the highest degree term. So to answer this question, I can really just ignore these completely. And the reason for that is that we're imagining x is really, really big. And so like x is like 1 billion. So if x is 1 billion, well then x is pretty big, but 1 billion to the 5th power is way bigger than just 1 billion. So the point is that this term here is going to dominate both of these other terms, because even though these other terms are really big, this term is going to be at least 1 billion times larger. Indeed, this term right here is at least 1 billion times larger than this term when x is 1 billion, and it's multiple billion times larger than this term. So when x goes to plus or minus infinity, you only have to look at the highest degree terms. And so if I think about, well, what's going to happen with this if I plug in a really big number? So if I plug in a really big number, I'm going to get a really, really big number times a -2. And a really, really big number times a -2, to me, just means that's a really, really negative number. If I think, again, if I think about a billion, this is going to be 1 billion to the 5th power times a -2. And I don't even know what to call that number, but all I know is it's a very, very, very negative number. So my answer to this would be negative infinity. That what's happening as x gets really, really, as x gets bigger and bigger and bigger, the leading term, since it has a -2 in front of it, is going to give me a negative infinity as an answer. So that would be my answer to that question. And let me see, I think maybe we have time to do another one, so hold on here. Okay, so now we got another end behavior question. It's a limit as x goes to negative infinity. So this time we're kind of interested in the left side, what's happening, what's the end behavior of this function on the left side. And this one is a rational expression. That is, a rational function is a polynomial divided by another polynomial. That's what we call a rational function, is a ratio of 2 polynomials. And so the good news is what we can do here is we can apply the same reasoning as we did before, that when you're dealing with end behavior, you only have to worry about the highest degree terms in the numerator and the denominator. So this guy, these guys don't matter in the numerator, and these guys don't matter in the denominator. So the only thing I care about really are these 2 terms here. And that's because, again, the x is getting really, really big. So the numerator terms are going to be dominated by this negative 6x cubed, and the denominator terms are going to be dominated by this negative 9x to the fourth when x gets really, really negative in this case. Okay, so then you can simplify, since we've knocked out all those other terms, we might as well simplify this. And we just simplify this to, let me see here, it's going to be 2 over 3x. That's just easy algebra there. And now I go back to the original limit, and I ask myself, okay, what happens when x gets really, really negative? So I imagine plugging in a number like negative 1 billion. So if I plug negative 1 billion into this, in for x, well, I'm going to get a negative number, clearly, because the numerator is positive and the denominator's, the numerator is positive and the denominator is going to be negative if x is negative 1 billion. But then the denominator is going to be like 3 billion and the numerator is just 2. And 2 divided by 1 billion is a very small number. If I have 2 cookies and I want to share them with 3 billion people, each person is going to get a very, very small piece of cookie, practically nothing. So the moral is that it looks like this is approaching 0. I mean, I guess you could say negative 0 if you wanted to be cheeky, because we do know it's negative, but it's going to 0. Because if it gets bigger, if I have more people, if I have 2 cookies and I need to share them with a trillion people, then everybody's getting even less cookie than they got before. So they're basically getting 0 cookie. Oh wait, I wrote the wrong thing there. This is not, I should not have written an equal sign. So bad on me. Those 2 things are not equal. What I should have put was a little limit arrow. As x goes to infinity, as x goes to negative infinity, that expression goes to 0. So anyway, so 0 would be my answer to what the end behavior. The end behavior. So in other words, this function has a horizontal asymptote. This function has a horizontal asymptote at y is equal to 0.